Okay, we're recording, so let's get back to our work. Okay, so here's our example problem. We have a new landowner, has a triangular piece of flat land she wishes to fence. Starting at the west corner, she measures the first side to be 80 meters long and the next to be 105 meters. These sides are represented as displacement vectors A from B in figure below. She then correctly calculates the length and orientation of the third side C. What is her result? Okay, I'm going to give you guys, I'm going to throw you guys a bone here. This is one of your homework problems for next week. This is topic 3. So just by paying attention and writing all this down, you can put this into your work for the assignment that this is contained in, and bam, you already got a homework problem done. Okay? So hopefully you can see the text on the projector screen so you can reference it if we need to. I know it's a little small, but I really wanted to fit all this on the same page. Okay, so we have this landowner. She's measuring for a fence. She's measured 2 segments of the fence already. She wants to know what the third segment's going to be. Okay, so the first segment she measured was 80 meters right here. Okay, and she measured that at an angle of 21 degrees below the x-axis. Okay, then from that point that she ended at, which is this dot, she then measured her next segment for fencing to be 105 meters. And she measured that at an 11-degree angle from the vertical, which you can see right here. Okay, what she wants to know is what is the final magnitude of the as the crow flies vector. Okay, so vector C, she wants to figure out what's that magnitude and what is its direction, what's theta, okay? So whenever you're solving problems like this, the first thing you got to do is you have to resolve your components. Okay, so step 1, resolve your x and y components using SOHCAHTOA. Okay, so if you've got a calculator on hand, please get that out, or if you've got one on your devices, you can pull that up. But you're going to want to be able to follow me along. So I want to focus in on our first vector, okay, which is the 80 meters measurement she took. So the 80 meters has an x component, which I just drew in blue, and it's got a y component, which we'll do in pink. Okay, and that's a right triangle. All right. So if I wanted to figure out what x and y were, we're going to need to use SOHCAHTOA. Okay? So if you think about it, I can figure out what x is by using cosine. Okay? So the cosine, if you remember from SOHCAHTOA, cosine stands for adjacent over hypotenuse. So the cosine of 21 degrees is equal to my adjacent side, which is x, I don't know it, over my hypotenuse, which is 80. Okay. Now, when you solve this equation for x, all you got to do is times that 80 over to the other side of the equal sign, and you get cosine of 21 times 80. If you're plugging this in, solving for x gives me that x is equal to about 74.7 meters. Okay? So all I did is I got x by itself by multiplying that 80 over into my calculator. Now make sure in your calculator that your calculator's in degree mode and not radian mode, or else you get it wrong. Okay? Similarly, I can figure out what my y component is using sine. Because remember, sine in SOHCAHTOA stands for opposite over hypotenuse. So my sine of 21 degrees is equal to my y component over 80 as well, because that's my hypotenuse. That hasn't changed. Okay, so when I type this in my calculator, if I'm trying to get y by itself, all I got to do is multiply that 80 over, just like before with the x. So sine of 21 degrees times by 80 gives me a y of 28.7. All right. Hopefully in the future I can get you guys more involved. I got to move quickly though because this is a pretty rich section. But for those of you who have calculators on hand, give me a thumbs up if you're seeing what I'm doing here. Okay, good. Good. Are there any questions up to this point? Okay. All right. So we're going to table those components that we just found. We're going to work on the next one now. So I'm going to do this next one in, let's say, orange. So the next vector was 105 meters at an angle of 11 degrees. So just like before, I'm going to draw I'm just going to sketch in my components. So I'm going a vertical distance of about that orange arrow is my vertical component of my next vector. And I'm going a horizontal component of this leg right here. So you can see we're creating another right triangle here by drawing those two orange lines in. Okay. So now, let's label which ones these are. So that the tall one is my y component because it's vertical. The short one is my x component because it's horizontal. And now I repeat the process over again. I'm going to do cosine and then sine to figure out what my x and y are. All right, I'm going to type this out just because I think I can be a little bit neater with typing. So if I take the sine of 11 degrees, that's going to be equal to my opposite over hypotenuse. Well, my opposite of my 11 in this case, if I go across the triangle from 11 degrees, I hit x. And that's going to be over my hypotenuse, which is 105 meters. So just be careful here that you don't mix this up. In this case over here, on the right-hand side, right here, cosine gave us x. Because the cosine, the x component was my adjacent side. But in the case over here that we're doing right now, sine is going to give me my x. Because my x component is now opposite my 11 degrees. So don't mix those up. You really got to be paying attention to which angles are opposite which components. Okay, so if I keep going, if I want to get my x by itself, sine of 11 degrees multiplied by that 105 gives me an x value of 20.0. Okay. Let's go ahead and do the cosine as well to get our y component. So the cosine of 11 degrees is equal to my y component over 105. So plug that in. Cosine of 11, multiply that 105 over, and I get that y is equal to about 103.1. Okay, so you can see what we're doing here. All we're doing is resolving these right triangles into their x and y components, and all of this is in preparation for the problem's final step. Okay, I'm going to do our final step in the lower right-hand corner of the screen. Let's make this green. Okay, so step 2, you're going to plug in your x and y components from all vectors into Pythag. Okay, so remember that Pythag is a squared plus b squared equals c squared. Okay, well, I'm going to revise that a little bit because we're not really dealing with a's and b's here. We're dealing with x's and y's. Okay, so it's going to look something like this. And I'm going to draw it symbolically first before I actually plug it in. So I don't know if you're familiar with sigma notation, but sigma notation just means add. So we're going to add all of our x components together. We're going to square them. Then we're going to add all of our y components together. So there's my sigma, meaning add. Add all of my y components together. I'm going to square them. And then that should be equal to c squared, right? My final, my resultant vector. So c squared. So this is really what I'm interested in, is c. Okay. Now, there's a little bit of a problem, though. And I should have brought this up earlier, but I'm just now spotting this. Remember the stuff we did over here on the left in pink? Remember that vectors have directionality to them. So because this pink work I did over here, look at this y right here. You see how this y is going below the x-axis? What happens to a number when you go below the x-axis? What does it become? It's negative, yeah. Okay, so this y value, I should have put a negative here, so I'm gonna sketch it in right now. So it's negative right there. Write that in if you didn't. So it's negative 28.7, and that's my mistake for forgetting to do that. Similarly, this x component up here in my second vector, you see how that x is going to the left? What happens to a number as you go to the left across the coordinate plane? It's negative, yeah. Whenever you're going left on a coordinate plane, you're getting more negative. So my x, in this case, should also be negative. So I'm going to put a little negative symbol there to represent negative 20. Okay? I'm glad I spotted that, or else this would have been very embarrassing. Okay, so I've got my components in. I've got my negative symbols in where they should be. Do not forget those negatives, guys, or else you will get the wrong answer. Now we're ready to plug everything in. I'm going to do this down below. I'm going to type this out just so it looks nice and neat. So the formula that I wrote to you in green with the sigma notation, I'm going to add all of my x components together. So my first x component was 74.7. I'm going to add that to my second x component, which was negative 20. Okay? I'm going to square that in a second. But my y components were negative 28.7. I'm going to add that to 103.1. That was my next y component. All right? And this should be equal to c squared. All right? So I'm going to put a square symbol there, square symbol here, square symbol here. So you can see that in my first parentheses, this is the sum of my x components. The second parentheses is the sum of my y components. And really all you got to do now is just some calculator work. So answer me this. How am I going to get c by itself in this equation? How do I undo that square? You got to square root it, yeah. Okay, so if I square root all this junk, that square is now gone from the right side of the equation. And this is what you're going to type into your calculator. Okay? So if you have your calculator, do this with me. Okay, so 74.7 plus a negative 20. I'm going to square that. I'm going to add that to negative 28.7 plus 103.1. I'm going to square that. And whatever that total gives me, I'm going to square root the entire thing. And I get an answer. Okay? How many of you are doing this with me? Raise your hand. Good. If you're not, please do this. Okay, just to get the practice in. Okay, so I get that my final vector is equal to 92.3 meters. Okay? Now, it's always a good idea at the very end of a problem to verify that your answer makes sense and is reasonable. So look at the original drawing. Could that vector C reasonably be about 92.3 meters? What do you guys think? Sure. Yeah. Yeah. I mean, our first one was 80. This vector C is a little bit longer than that. Our second vector was 105. Our vector C is a little bit shorter than that. This totally makes sense. This could be 92.3. So that's an answer that I'm happy with. Okay. Now we finished one of our tasks. We figured out what vector C's magnitude was. So we can check this off. But we still need to figure out what theta was. All right. So this is where that formula comes in that I had you guys write down about 20 minutes ago. Can someone raise your hand or just shout it out and tell me what that formula was for theta? I'll give you a hint. It had a inverse tan involved. Okay, so say it a little bit louder.
Negative tangent?
Good. Inverse tan.
Okay, a sub y divided by a sub x.
Okay, good. All right, so let's plug that in. So, and let me do this in a different color just so we can separate our work out. We'll do this in red. So we're going to do the inverse tan. So tan with a little -1 on top. And we're going to do our y component over our x component. Okay? So our y component is written right here. It's the sum of these two numbers, -28.7 and 103.1. Okay? So if I plug in -28.7 plus 103.1, I get that my y component is 74.4. And that's going to be over my total x component, which is right here. So 74.7, I'm going to add that to -20, and I get 54.7. 54.7. Okay, so when I plug this into my calculator, now remember, on your calculator, inverse tangent is usually a secondary function. So you got to hit second tan to access the inverse tan. Okay, so I'm going to type in second tan. I'm going to plug in 74.4 divided by 54.7. And I get an answer for theta that's 53.7 degrees. Okay? So stop what you're doing and look at the screen for a second. I want you to see something. This angle right here, this is our theta we just figured out. So this is 53.7. Now sometimes physics problems will try to confuse you, because if you look near the top of the problem, they drew our theta question mark as this angle up here. Why in the world would they do that? What's the relationship between those two purple angles I just outlined for you? They're the same, yeah. How do we know they're the same? I heard someone saying, I forget what it's called. It's probably because you learned geometry. It's called alternate interior angles. Do you remember that?
Yes.
No, I hear you no, I hear yes. Okay. So just keep in mind, even though they wrote our angle of interest up there really weirdly, it's the same thing. Okay? So that is our answer for theta. Our answer for the magnitude was down here. We are done with this problem. Okay? Now, I can see what you guys were saying earlier today. That young lady who mentioned that the honors work may be a little bit more advanced than what you guys are used to. This is a pretty difficult problem. So I might need to go in and adjust some of the problems so that you're not doing so much of this math over and over and over again. But if you can at least be comfortable with this problem and understand the math that we use to get to each of these steps, you're going to be in great shape. Okay? All right. How are we doing? Who has questions? Is this pretty intimidating? Is it doable? Okay, I would agree. It's very doable as long as you keep yourself organized and as long as you follow these two steps. Always resolve your components first and then plug them all into Python. And I guess I should have written a step 3 for the angle. Let me do that real quick. So step 3, I'll just plug that in right here at the bottom. Step 3 is plug in components into equation for theta. That's step 3. Let me make that red so it matches with the work I did there. All right. Ooh, that was exhausting. Okay, I'm going to erase all this work in a moment. And that moment is now, okay? So any last burning questions, speak now or forever hold your peace. Okay. All right. How much time do we got left? 10 minutes?
Yeah.
Okay. So we're going to get through most everything I wanted to go over today. Let me just say this down here. The last thing I wanted to go over, section 5 of this agenda, this is basically the exact same thing we just did. The only difference is that section 5 in your reading talks about multiple frames of reference. So make sure you read up on that. But when you boil it all down, it's the exact same thing we just did as far as the math is concerned. Okay. But section 4 is a little bit different. Okay. So if you can see my screen, you'll see these equations on the screen. These should look familiar because I covered these in my video last week. Okay, so these are what we call kinematic equations. All right, so whenever I reference kinematic equations, this is them. Now, I don't know if you guys heard on the video, but I'm not going to expect you to memorize these equations for any quizzes or exams. You will always be able to use an equation sheet to reference these, so don't try and memorize these. And in my video last week, I mentioned to you guys what each of these variables means. So go back if you've forgotten already and jot down real quick like what x meant, what v bar meant, what v0 meant. Okay? So that you can always know which equation to use in which scenario. Okay? Now, I'm not going to have time to get to my example problem because I'm still in the explaining phase of this section. So I might need to make a video on that problem and post it tonight. But let's at least go over the basics of section 4. So remember, you must always resolve components. Section 4 is about projectile motion. Okay, so remember projectiles, if you ever heard about a projectile, it's just something that is launched into the air and is subject to the force of gravity. So for example, let's say that I have a bow and arrow, and I'm shooting this arrow into the air. It's gonna fly into the air, gravity's going to take hold of it, it's going to come back down like this. Okay? But we can measure the velocity of the arrow using vectors. So in a lot of these problems, they'll give you what the starting velocity was of the arrow as a vector. So I just drew this in as a pink arrow. So they will give you velocity of a projectile as a vector. Okay, and remember, with any vector problem, your first step is always resolve your components first. So when you come to these problems, you got to break out that SOHCAHTOA. Figure out what the x component is. Figure out what the y component is. Okay? Where the equations come into play is with your components, okay? So after you get your components, I just want to highlight something I typed in here. You need components to be independent of each other to plug into equations in your next step. So once your components are separate, okay, you're going to make equations for your x component, and you're going to make equations for your y component. Okay? So use these equations separately for your x and y components. Okay, I just lost video feed. Are you guys still there? Is anybody still there? Okay, Mr. Schmitz, are you there? Can you hear me? Okay, if you can hear me, I'm just going to keep going. Just give my closing thoughts, and then we'll wrap it up and call it a day. Are you back?
Yes.
Did I lose you for a second?
Yeah.
Okay.
Just a couple minutes left, and the battery on this computer might die.
Okay. So I guess my last thought, and I'll make a video of the example that's listed here. But my point is, you always resolve your components because when you get your components resolved into x's and y's, you need to use the equation that you need separately for your x component and for your y component. So let me just give you a hint, kind of a teaser trailer for what you're going to be doing in the example down below. So I'm just going to give it away. In the example below about a projectile, it's going to be asking you, what are the x and y distances from where the projectile was launched? So you see on this question, they're asking us for distances. Well, this equation right here is a really good pick for calculating distance, because remember, x stands for positions or displacement, distances. Okay? So I'm going to need to use this equation once for the x component, and then once for the y component. Okay, so use this equation in the example below once for the x, and then again for the y components. And when you do that, you're going to get an answer that you can then plug into Pythag and then do what we did in the previous example. Can you guys still hear me? I lost video again. Okay, I can't hear you. I can't see you. You've only got a couple minutes left, so I'm just going to call it a day. Stay tuned for that video example. I'll post that later tonight, okay? Bye.